Windows half one, or I think it's probably similar to model case. Okay.
Anyway,
That's a very small.
it's a very small domain, but it certainly is very interesting. So,
But I think the nonlinear term is going to average out. He said it changes within hours, right? It changes sign.
yeah, but it doesn't.
All right, so all century set up. So how is your let me
He
check
said it would
the
average
input
out.
standard, so you don't have to worry
He
about
actually
that.
did a composite. It doesn't
Yeah,
average
you can start the.
Oh, yeah. Thanks.
So I remember saying that.
So after finishing your talk, I'll do the Google this one, okay?
Oh, yeah.
I'll help you to set it up.
Oh, yeah.
I'm good. Just put it here to close it.
Oh, this window. Okay.
To further the-
Yeah, the surgery.
Oh, sorry.
Really surprised. We're going to add a lot of noise to the data. Okay, so you need introduction or no? I think
Oh, yeah.
You don't need introduction anymore, right? You got, everybody know you now.
Yeah, actually, I prepared some very brief introduction.
Okay, good.
So first of all, yeah, I would like to express my gratitude to all of you, especially to Professor Chan, to give me a great opportunity to come here and do my research. And so this is my brief self-introduction. My name is Satoru Kojima, and I'm in second year of PhD course. This is a picture when I joined the research cruise last year and over the Kuroshio extension. And my supervisor is Professor Hisashi Nakamura in Tokyo University, and who is at the center of this picture. And actually, here is Professor Chan. So actually,
Yeah, I remember that.
also he visited us last year for 2 months. Yeah, and I really enjoyed talking with him. And then now I'm here. Okay. So I'll move on to my research, and this is the contents of my talk today. So the first I will introduce a background of my research, and then I will talk about the summertime atmospheric response and then intertime atmospheric response, and finally I will sum up my talk. Okay, so first I'm talking about the previous studies. So in the previous studies, especially for the classic studies of the responses to SSD anomalies, so the research has been investigated. So the response is investigated with observational data, analysis data, and the models. And here is the knowledge obtained in previous studies about the SSD anomaly in tropics. Their influence onto the mid-latitude atmosphere is very strong. On the contrary, the extratropical SSD anomalies have only weak influence on the mid-latitude atmosphere, and because of the remote influence from tropics and the large mid-latitude internal variability. So this is a figure by Lau on 1997, and this is a response to equatorial Pacific SSD anomalies. So this is a model response, and here you can see a very clear response to the SSD anomalies, and here is a response to only mid-latitude North Pacific SSD anomalies. So the response is not clear, and this study suggests the SSD anomalies in equatorial Pacific have a very strong.
Do you know if anybody made attempt to do I know that if you just do, you do a EOF analysis on the sea level height, or sea level pressure.
Oh, yeah.
The dominant pattern is this Aleutian low.
Oh, yeah.
Right? So did anybody trying to, let's say, take the years where there's no tropical forcing, and just look at the the variability in latitudes. During the period there's no obvious tropical forcing, and to see whether the pattern would be also a illusion low.
So you mean that so without the tropical forcing?
Yeah, that's right. I mean, I think a lot of the illusion low come from the tropics.
Yeah, yeah. Actually,
and that's the problem.
Actually, I did the analysis you suggested, and actually the PNA-like signal here is partly associated with the tropical forcing. But,
so even if you isolate the tropical forcing, if you look the first leading UF, it still looks like this.
Yeah,
okay,
right. And actually the location of this signal is slightly shifted compared to where?
Shifted towards where?
I remember that the shifted to the eastward.
Oh, that's great. Because that's exactly what I'm looking for.
Oh.
Because all the model simulation right now, when we force with high resolution SST in the thing, we don't get the illusion low. We get the pattern shifted eastward. We all get that. I mean, at least I've seen 3 models now. The Latif was giving a seminar. He shows a pattern like that.
Oh, yeah.
And our original model also shows a shifted eastward pattern. And then I think a recent study, Matt Newman also showed a pattern which is shifted eastward. And I'm wondering the reason we don't see that in the direct observation, whether it's because of the tropical influence. So. If we have a long enough observations, we should be able to isolate the tropical forcing from the extratropical. Maybe we're getting a pattern more like what we're seeing.
Actually, this is another work I'm doing now, and so the variability of this PNA-like signal, it should be divided to the atmospheric internal variability.
Yeah. I'm so glad. I like to see your results. If you already done it, you said was slightly shifted. Because I asked Latif exactly the same question. I don't know the answer.
Oh, but in his case, he has so many different things happen.
I know. In his case, it's complicated, but he only, it's never sure. But in our regional model, it's very clear.
Yeah. So it is more that actually, so the EOF pattern obtained by the observational data is slightly different and not identical to the remote inference from the tropics.
Okay.
Actually.
Good. Good. I like to see that actually.
Oh, yeah. Okay. All right. Let's move into this next page, and about the experiment with HCMs. This is a few knowledge thing in previous studies, and it is revealed that the atmospheric response depends on the location, strength of SST anomalies and background staging models. And they also found difficulties in obtaining robust response in summer. This is the first motivation for my research. But I think it is influenced by the use of coarse resolution model and SST data. Because the typical model resolution at that time is T142, so this is corresponding to the 2.5 degree. So very coarse resolution, and the mid-latitude ocean is abundant in fine-scale frontal structures and eddies, so insufficient to resolve and present there. This resolution is sufficient. And the previous studies, particularly the recent previous studies, is focusing on the non-specific subarctic frontal zone. And this is a region where meridional SST gradient, shown here, is very tight, and it is prominent in winter season, and is expected to anchor the storm track. And so this is the study of my supervisor, but there is a decadal scale SST variability shown here. In SST, in wintertime, subarctic frontal zone, and surprisingly, it has a weak simultaneous correlation with the tropical forcing, and it is also suggested that it has a meridional shift of ocean front. That it is followed by the meridional shift of the front, and recent studies about the atmospheric response to the SST anomalies, mid-latitude SST anomalies, is focusing on this subarctic frontal zone variability. For example, this is a picture in the Taguchi et al. 2012. They found the atmospheric response to preceding SSD anomalies over subarctic frontal zone in midwinter, like this, as the weakening of the pollution load associated with warming and the frontal zone. And this paper, Frankton et al., also suggested that the wintertime atmospheric response to preceding meridional shift of the shield front. But yeah, these studies are based on observational and coupled model experiments. So I think these are not solid evidence to the ocean forcing to the atmosphere. So it is to be tested with AGC experiments. So this is the second motivation of my talk. Okay, so let's move on to the result. And first, I am talking about summertime stuff. Okay. This is the data and the motivation and the experimental design. So first, summertime response in mid-latitude is difficult to obtain in models. I suggested by the previous studies. So I'm focusing on the stronger SSD anomalies. In fact, in 2011, somewhere in autumn, the most prominent one SSD anomalies shown here was observed since 1982 over North Pacific. So here is SSD anomalies up to 3 or more degree, and here is the frontal region suggested by the contours, black contours, the SSD, Grand Torgamine SSD. So, and this is followed by the anticyclonic anomaly here in October. And in addition to this, tropical SSD anomaly is not so prominent in this year. So, okay. I conducted the experiment for this, and the observed atmospheric anomaly at that time is response or not. This is my question. And about the model one data and the experiment design. So the AGCM I used is APHES. APHES is AGCM developed in the Jamstack, and the horizontal resolution is 1 degree. So 1 degree is not so high, but kind of a typical resolution of the current IPCC models, or so. And I use a reanalysis. JR is Japan reanalysis, and the OSST. OSST is observational SST. And we conducted in total 3 ensemble experiments. The first one is a chromatological mean experiment with a chromatological mean SST. And the second one is a mid-latitude hindcast experiment with the positive SST anomalies over the North Pacific, only over the North Pacific. And the last one is a tropical hindcast experiment in which the observed SST is prescribed over only tropics. And each has 10 members initialized around 1st June to the end of October. The difference is one. These ensemble mean are considered as a response.
Did you use the daily mean?
So this is a good question, and actually I use a monthly mean SST, and this is interpolated to the daily basis. But the SST had almost no daily variability. So it is related to the lattice store. Like this. So only over the North Pacific in mid-latitude hindcast experiment, and the tropical hindcast experiment only over the tropics. Okay. So first I will show the summertime result. So as a representative of the summertime, I only show the dry case here, and this is the observed SLP anomaly and here is the mixed latitude hindguess SLB response. So you can see the deep unsegmented anomaly or the SSD anomaly indicated by the red hatch here in the observational data, but you can see the shallow segment response here and the SSD anomaly here. And so the color is 95% confidence level, and so it is clear that these two is not identical, and there is a large discrepancy between them. And the reason maybe one of the reason is maybe a strong Rossby wave propagation from upstream was observed in July, and in association with this, ocean was heated by atmosphere in observation. This is a reversed relationship to the model, and a similar situation is occurred in September. So I mean that causality, the kind of a causality is reversed in the summertime case. So it is not bad to simply compare these two. And
so in the Handcast experiment, both the tropics and exotropics are used for the atmosphere.
Oh yeah.
So in this experiment, you have both the tropical forcing and the exotropic.
Yeah, of course, there are two Handcast experiments.
Right. So in this Handcast experiment, is the tropical forcing included or not included?
Not included.
But this one is not included.
Yeah, for just this SSD.
Okay.
Okay. And in addition to these, the summertime background westerly is weak or even easterly, so this is not favorable situation to get a stationary Rossby wave response here. So for model. Okay, and so the summertime case is not so good for me to investigate because the causality is reversed. So I move on to the October case. So in October, this is a height anomaly at 250. The lower panels is SLB anomalies, and so we obtained a very nice anticyclonic response here, consistent with observation. And actually, in October, there is a very weak, only very weak, and almost no Rossby wave injection from upstream. So this SSD anomaly is not influenced simultaneously here in October. And this result suggests a possible contribution of warm SSD anomalies here to the formation of the anticyclonic anomaly. Here. And for transient eddies, this is a figure of current local mean hyperspherical height anomaly, root mean square of hyperspherical height anomaly at 250, indicated by black counters. So the position and the strength of the storm track is very consistent with observation in the model. This is the current local mean, and the anomaly is superimposed to this. The warm color is a positive storm track activity. So you can see that the storm track is located here, and in October, storm track is shifted northward and strengthened around here. So this is suggested that it has a feedback forcing to the mean state. And in addition to this, this modulation, the strengthening and the northward shift of the storm track is consistent with enhanced SSD gradient here. So that along the northern flank of the warm SSD anomaly, the radial SSD gradient is become tighter here.
So let me clarify. So this is the anomaly in a particular month, right?
Yeah.
It's a particular. It's only in October.
Sure. Yeah.
Okay.
So you mean that in this experiment?
No. What you're showing here. What do you mean by anomaly? Anomaly in October
Yeah, normally in October.
only, in 1 month.
With respect to a base period,
Yeah, so for observation, the base the period is about 30 years, and the SST climatology is derived from the same period.
so just the 1 month compared to those 30
Yeah.
months.
And for the model, of course, you just read relative to the climatology would be normally a reference to the experiment without SST force.
Yeah. Oh, right. And so yeah, it is suggested that this modulation have a feedback forcing onto the mean state like this. So this is a very classical paper by Lau and Pioneer. So the transient eddies act to force and cyclonic tendency to the south. This is a key Frank's contribution, and this is a Bautista Frank's contribution. If these two contributions combined, the anticyclone is tend to be forced to the south. So how about the feedback caused by the modulation in October 2011? So I can calculate this feedback forcing by solving three-dimensional tendency equation, and here is the result. So the color is a height tendency, evaluated by the three-dimensional height tendency equation by the transient eddy modulation, and the black contour is the same as the monthly mean anomalies. So in both in the observation and the mid-latitude highly gaseous experiment, the feedback forcing by transient eddies is anticyclonic, anomalous anticyclonic in both in the upper troposphere and the lower troposphere, and this is strong, and this is able to replenish monthly anomalies in several days. This is a color about the unit is a meter per day. Okay, so this suggests the importance of transient eddy feedback forcing in the observed anticyclonic response in October 2011. And furthermore, I want to compare this feedback forcing with energy conversion from mean state. So I conducted the energy budget analysis. So these two is compared by this energy budget analysis. So this is a kind of schematic diagram of the energy budget. So here is anomalous energy associated with monthly mean anomaly, and here is a mean state associated with mean state. And this monthly mean anomalous energy is related to the here mean state and generation by direct heating and feedback from transient eddies, and these arrows is divided into two parts. The one part is kinetic energy conversion, and the other one is available potential energy conversion or generation. And these energy conversion and generation terms are integrated around the response and the form surface to 100 hectopascal level here. And so how many days each term needs to replenish total anomalous energy, so kind of efficiency associated with the response is calculated for mid-latitude high gaseous experiment. So the result is here. Here I only show the measured terms in October 2011, and you can see that the largest contribution of transient eddy feedback forcing here. The number is number here is just energy conversion rate. The unit is here. So this is the largest among these. And in the observation, this here APE conversion, and in the mid-latitude high gas experiment, both APE and the KE conversion are important. And here is how many days each terms can replenish the total anomalous energy, and we can see here that these terms are able to replenish the total anomalous energy in about 1 month. So this is indicative of the characteristic as a dynamical mode of the anomaly and the response to the inherent to the chromatographic mean state. Okay.
So what's the error bar? I mean, you have a 10-member ensemble, right?
Yeah. So you mean that
What's the inter ensemble deviation on these numbers?
sorry, actually, I don't investigate the error bar for this. Yeah, but I think the response, the model response, is quite robust for this experiment.
It would be nice to see, you know, what. I mean, I'm sure you're going to see a large deviations from one experiment. Yeah.
Also for this.
For these numbers, yeah. For each ensemble member. You're doing this calculation for each ensemble member, right? So you take the ensemble mean at the end of the year. And simply wants to see what's the spread among the ensemble members.
This number.
Yeah.
Yeah. Okay. I will calculate the model the ensemble spread for this. Okay. Yeah, and the energy generation through diabatic processes is small. And so here is the remote inference from tropics. So this is a result for the mid-latitude Honeycastle experiment again, and here is a tropical Honeycastle experiment. So you can see that the anticyclonic anomaly here is the same sense as this experiment, but this is weaker and less significant compared to the mid-latitude Honeycastle experiment. And this is a linear regression onto the -3.4 index in the observation. So you can see here the anticyclonic anomalies associated with the linear-like situation here. So I mean that the tropical Honeycastle experiment result here is consistent with observational signal associated with ENSO. So the tropical Honeycastle experiment is okay. I mean, so this is a summary for the summertime experiment. So I conducted the sensitivity experiment with AGCM for 2011 summertime SSD anomaly, and for summer AGCM fails to produce the observed anomaly, and in 2011 the strong Rossby wave propagation from upstream was observed, and the atmosphere is heated by atmosphere heated ocean, so causality is reversed. And the comparison of model response and observed anomaly is not valid. And our model results suggest that the response to SSD anomaly, the mid-latitude SSD anomaly in summer, is weak. And for October, our AGCM experiment will produce this observed anomaly. And subarctic frontal zone SSD anomaly can force atmospheric basin scale atmospheric response in October. And in 2011, no Rossby wave injection was observed. So in observation, ocean forced atmosphere, so the causality is not robust. And
so did you look at the flux?
Yeah, of course.
Does it change sign between summer and fall?
Yeah. Actually,
flux.
Yeah, actually in summer, so the anomalous turbulent heat flux around the SSD anomaly is downward. So the atmosphere anomalously heated the ocean. But in October, the flux is not so strong, but upward sense.
So you can see that in the. So do you use reanalysis? How did you get the observed flux?
I use OA flux.
Okay.
Yeah, so not reanalysis. But the result is not so different from the reanalysis, but the sense is upward.
It would be good to show that, to be interesting to see that fluxes. It's not easy to see a situation where the ocean, large scale forcing of the atmosphere by the ocean. It's not easy to see that.
Yeah. I see. Okay. And the atmosphere anomaly and the response is largely maintained by the transient feedback forcing, and energy conversion is also important, and this is suggestive of a dynamical mode characteristic. And the remote inference from tropics is weaker than observed anomaly. So this with latitude SST anomaly is most important for this particular October. Okay, and in addition to this, I investigated seasonal evolution of background state. So this is a figure of a zonal mean, the mean state of wind, zonal wind velocity at 250, and the mean high-pass filter root mean square of high-pass filter meridional wind at 250. Also, the black contours is a wind speed, and the colors is the kind of the strength of the storm track and the position, and the variables is zonally averaged in this longitudinal band, and the kind of Hochmel diagram. So you can see that the southward migration and the strengthening of the westerly, the mean westerlies and the storm track here. So this is August, and here is October. And the red contours here is the SST anomalies in 2011. So in October, the SST anomaly is stronger in this longitudinal band. So around here, you can see the nice collocation of the SST anomalies and the current of the mean westerlies and the storm track. So in October, SST anomalies may be easily reflected in the storm track modulation, and this leads to the difference of the model response due to the different transient feedback forcing in midsummer, and October. So the finally leads to this difference. Okay, this is the summertime response, and now I'm move on to the wintertime case. So the wintertime atmosphere response. Okay. So for winter, remote inference from tropics is very strong. So I'm focusing on the ocean-induced decadal scale SST anomalies over subarctic frontal zone. This is a kind of same strategy of the previous studies I showed. And for SST anomalies, I use ICOAS because to obtain a longer time period of SST anomaly, and these two periods are considered as the warm and cold period decadal variability, and half of the difference between these two is considered as amplitude of the decadal variability, and this is added to characteristic mean SST only over subarctic frontal zone, and I found that the difference in the tropics is weak for these two periods, because these two periods is the 5 year average, and so like this. So the only the SST anomaly is added only over this subarctic frontal zone, and the current of the mean SST is OSST, because OSST can resolve the fine scale structure current of the mean structure in subarctic frontal zone. And for a wintertime experiment, to obtain a clear response, the amplitude is multiplied by 3, and so this is a kind of a so the inflated SST anomaly in this experiment, and each has 10 members started from October to March, and in total, I conducted 3 ensemble experiments. The first one is the Cranberg mean hindcast, Cranberg mean control 1, and the second one the positive SST anomaly hindcast experiment, and the last one is a negative SST anomaly hindcast experiment. But today, so I will talk about the only positive one, because the negative one is the result is very complicated, and I'm doing that. And I use the analysis for the winter time. The J55 is used. Okay. The result is here. I will show the January atmospheric circulation anomalies, and here is the observational anomalies, and here is a positive handicap experiment response. And the upper panel is a anomalies at 300 hectopascal level, and the lower panel is the XLP anomalies and the response. So actually, here is a anticyclonic, significant anticyclonic response in model, and actually the location is slightly northwestward shifted, but we can obtain a significant response here. So this result suggests the possibility of atmospheric response to decadal scale SST anomalies associated with the variability of the oceanic frontal zone here. And I investigated the modulation with transient eddy activity again. So you can see that in the observation, the storm track activity is suppressed around here in the upper level and the lower level, and this suppression is kind of reproduced in our model. The response is slightly westward shifted, but the sense is the same. And this response is consistent with suppressed radon SST gradient around here. So the southern flank of the SST anomaly, warm SST anomaly. And the feedback forcing by this modulation is calculated again, and this is a result. So for observation, the feedback forcing is again the anomalous anticyclonic height tendency around here, and actually the monthly mean anomaly indicated by the black contours is well propagated the positive height, anomalous height tendency. So you can see the transient eddy feedback forcing is maybe positive, but here is a model response, and you can see that feedback forcing is weak and not well propagated with the monthly anomaly. Okay, so this suggests that feedback forcing by transient eddies is not effective for the model response. And I conducted again the energy budget analysis. Here is the result. So note that here is I showed the number here is efficiency. The unit is day, so shorter is more efficient for this. Okay, and measure terms, only measure terms are shown here. The terms are the same for the Samantha case. And this table suggests that the largest contribution of energy conversion from in state here, the red terms, and this is again the indicator of the characteristic as a dynamical mode inherent to the parameter of the mean state in winter. And in the observation, both kinetic energy and the available potential energy conversion are important, but for model, only available potential energy conversion is dominant. The slightly different mechanism. And in addition to this, the transient eddy feedback forcing is not substantial for observation of the model. But I think this act to modify the particle structure of response. Not effective.
So what does the negative mean?
Negative is
the forcing is the other way around.
Oh yeah, so in model, the transient eddy feedback forcing acts to dissipate the monthly mean structure.
So okay.
Yeah, but this term is not so large. So this can be neglected. And furthermore, I investigated the reason why this change is occurred for these two observational anomalies and the positive experiment. So this is a figure for the kinetic energy conversion, this is only the monthly wind anomaly, and the brown content is a westerly wind in January. So I kind of a westerly jet here. So you can see in the observation, the dipole-like anomaly and the cyclonic anomaly is traveling jet immediate region here. So here the zonal gradient of the zonal wind speed is very large. But in the positive experiment, the response is westward shifted, and this is struggling jet core region. So the zonal gradient of the zonal wind speed is not so large, and then the kinetic energy conversion rate is superimposed onto this, and then you can see here the energy conversion from the westerly jet is quite effective. It is consistent with the PNA-like structure of this anomaly, but for the positive experiment, the energy conversion from westerly jet is ineffective, and this is maybe related to the WP-like structure of this response. So the change, the difference of the kinetic energy conversion rate is related to the displacement of this response. And I want to know why the response is shifted westward. So this is a figure about the relationship between the with the atmospheric internal variability of the atmospheric response. So actually, for the coupled model under observations following this paper, the internal variability is estimated as monthly difference from DGF mean for each month. And this is the observational data. Here is a couple model used in the previous studies, Taguchi et al. 2012. And you can see in the observation, here is the PNA-like atmospheric internal variability. And the blue contour is a westerly wind, westerly wind speed. And here is the coupled model. So you can see here the color is internal variability, and this CGCN will reproduce the PNA-like internal variability here. And the response is collocated, indicated by the black cross here, the center of the anomaly in January. Is indicated by this black cross, and this anomaly at the center of the anomaly is well correlated with this internal variability. On the other hand, in our model HCM, the center of action is the internal variability is Bering Sea, located at Bering Sea, and the PNA-like signal here is very weak, and the response is also located at the Bering Sea here. So kind of wave collocation is clear here. So unfortunately, our model have only weak PNA-like signal, but from this one, from this result, the atmospheric response may depend on internal variability strongly for wintertime atmospheric response. Okay. So this is a summary for wintertime atmospheric response. So significant atmospheric response is simulated in the experiment only with SST anomalies. Of course, kind of inflated SST anomalies, but there were no specific subarctic frontal zone, and this is suggestive of oceanic forcing onto atmosphere in winter. And the energy conversion from background state is most important for the atmospheric response. So this is again indicative of a characteristic mode characteristic as a dynamical mode. And the difference in relative position of the anticyclonic response to the climatological mean jet is the different importance of the kinetic energy conversion, so different mechanism of the maintenance. And this is related to the PNA-like, the WP-like response. And this is also suggested that large-scale atmospheric response the wintertime atmospheric response may depend on dominant internal variability, atmospheric internal variability. Okay, and so the summary, yeah. So this is the overall summary. So atmospheric response to mid-latitude SST anomalies is here divided into 3 parts. For summer, there is only weak response to the SST anomalies, mid-latitude SST anomalies, and this is related to the weak transient eddy feedback forcing, and I think this is related to the shallow sunplane. So the ocean SST anomaly is followed by only the very small amount of heat capacity. And for October, the SST anomalies over the frontal region can force atmospheric response, and transient eddy feedback forcing is important, and large energy conversion from background state is important, and this is suggestive of the dynamical mode of the response. And for winter time, again the SST anomaly can force the response, atmospheric response, and the transient eddy feedback forcing is not important, so important, and the response have a characteristic as a dynamical mode, and the response, the location, the position of the response is tend to depend on the dominant internal variability, and the change between these two is related to the seasonal evolution of background state. So the southward shift, southward migration of the current of the mean westerlies and the storm track. Okay. Oh, so this is a short discussion, but I mean, here is a very recent paper by the NCAR team. So they, suggest that so the only 0.25 degree model can produce the atmospheric response consistent with observations. Here is a January anomaly at 300 hectopascal level, and here is a 1 degree model. So the 1 degree model cannot reproduce the basin scale atmospheric response to the SST anomalies associated with the frontal shift. But they failed to reproduce the weakening in February. The weakening in February is suggested by the previous studies by the Jamtek Chi. And this is another recent previous studies. So this study suggests that the background westerlies are influenced through transient feedback forcing, of course, and they use the 2 different horizontal resolution model. And here is the westerly wind speed, the change between the 20 kilometer model and the 120 kilometer model. So the higher resolution model, in the higher resolution model, the westerly wind speed is enhanced. Here, for mid-latitude, westerly wind speed is enhanced, so jet is enhanced. So the question is the model resolution of our model is enough? And I think the representation of transient eddies are probably better in higher resolution models, of course. But response in October 2011 is what we produced in our AGCM, even 1 degree. So I think that with this resolution about 1 degree, essential processes seem to be presented well for this. Okay, so some cases, at least for some cases, the 1 degree is okay. But it is possible that the change in representation of transient eddies can affect background westerlies. So this has a possible modification of dominant internal variability. So I think I should conduct the experiment with high resolution model, particularly high resolution regional model, because by regional model, the chronological mean state is not so different compared to the observational chronological mean state. Okay, so I want to do some analysis by the regional model, the Professor Chan's regional model. Okay, thank you.
Very nice. Okay, thank you.
Aren't you worried about the boundary condition that it constrain the mode?
Oh, so you mean the
Regional model.
which experiment?
The regional model.
A regional model.
Yeah.
We have to use boundary conditions for the region.
So you mean the which data or?
Yeah, it can constrain behavior near the boundary.
So using the regional model.
Yeah.
So actually, so for example, yeah, of course, the many experiments is possible, and
Maybe it could be a channel model or something like that.
channel model.
Channel.
Channel. Yeah.
You won't get a boundary in one direction.
Channel model. Yeah.
I mean, it seemed to me that if you go back to your summary slide, it seemed to me that in October case, for example, I think you only show a particular year, right?
Yeah.
I mean, I'm not sure if you can generalize your conclusions
Yeah.
in
This is a
such
good
way
question.
that in all Octobers,
Yeah.
they generate feedback.
Yeah. Actually, our result is our result suggests in some cases in which the inference from the upstream is weak.
Right.
If the upstream inference, the inference from upstream is weak.
But you haven't done all the cases where the upstream inference weak in October to really prove that point. Right. I mean, a lot of this thing, I think to me, seems to be more speculative rather than.
Could you test that using your regional model? Or like
In principle, you can. You can control the upward. Control the boundary conditions. You can test that.
Yeah, actually.
But I think before you make this thing as a general conclusion, I think you ought to be careful. And then the winter case, I think at this point is also a hypothesis. You don't really know. Obviously, your model has a problem.
Yeah.
The mean jet is bad, and assuming I'm not sure how you're going to. I don't know how you're going to blame the internal variability. I mean, one could argue the jet structure is also bad. It could be a mean flow problem rather than the internal variability problem.
Yeah. Actually, I think the problem of the internal variability is related to the mean flow problem, and you can see the mean flow is.
Although I don't know the mean flow. I mean, if you calculate the mean baryoconicity.
Mean baryoconicity.
Yeah, I mean, if you look at the winter mean, if you calculate the ED growth rate.
Oh yeah.
It's probably okay because I think the jet position in the western part of the domain is actually okay.
With this one here. Yeah, I see. Yeah.
So which means that if we think about the classic theory, the internal variability is more determined by the strong baryocanonical zone, right?
Yeah.
So from that respect, the baryocanonic stability is probably not bad in the model. It's really the downstream, which is really bad.
Yeah.
So I'm not exactly sure why the downstream, which is really forced, which is really forced by the eddies, most likely in the eastern part of the
here.
Yeah.
Yeah.
And that part seems to be bad, which is really surprising to me because most of the model I would expect the eddy forcing part should be actually pretty good. It's actually difficult part is actually getting the genesis right.
Oh yeah.
So I'm not entirely sure. Your speculation is entirely. I would say that what you're writing down as a conclusion, I would put it cautiously as really a hypothesis. Rather than a definitive conclusion.
Yeah. Thank you. Yeah, I will. Yeah, take care of it.
Because I mean, if you cut off the dateline, for example, if I ignore the dateline, I look the mean jet.
Flow is good.
They actually look very good.
Yeah.
Right. I mean that that's where you would expect most of the swarm actually got generated.
No, so you mean that the kind of a dissipation or something of the 280?
That's right. I think somehow it's the 84th, the mean circulation part is not right in your model. But I don't know exactly. I mean, you might want to compute the E vectors or the eddy vorticity convergence or something, and to see how much the eddy forcing in the eastern part is actually simulated. Right? It could be that somehow, the waves is not propagating in the right direction. For some reason.
No, so you mean that so the transient eddy activity, also the effect from the transient eddy activity, the terms of the mean state.
Right. It's probably
yeah. I think you're right.
Yeah.
Actually, the internal variability problem and the music problem is very serious.
Okay, well, thank you very much. I think you can discuss with anybody here, and I'm sure that we can help you to set up the regional model experiment.
Yeah.
I do have a question. Can I ask a question?
Okay, thanks.
Feel free to talk.
Hello?
Yeah.
Okay.
Hello?
Thank you.
Thank you very much.
Yeah. All right.
Hello?
Actually, I forgot to ask a remote audience. Are there anybody there?
Yes.
Let's see. Where's the mouse?
Is the
Where's the cursor?
is it Chris? Chris, do you have any questions?
No,
Chris.
but I think it sounds like Raffaele does.
Yes. But I don't know if they can hear me.
I don't think they can hear us.
Here. Here?
Yeah. No,
Can you hear us?
Hello? Yes. Can you hear me?
Yes,
Hello?
I can hear you. Yeah.
Oh, okay, good.
Yeah,
So,
but I don't think they can hear us.
So there are a lot of people there, but I don't know.
Sorry, you guys can go. You don't have to.
Is there any
That's okay.
questions from
No problem.
remote
It wasn't-
participants?
Grab some cookies. Right?
Where's your volume count? Settings.
Crux of the papers, do you think I should just send
Send to me first.
真的重复我吗？
And then do the calculation. How to do
Can you increase the volume?
the next one.
This warning?
Volume, the
Very
sound
easy to do.
volume.
Right? You already did the classic acno pumping.
Yeah. Yeah.
Which doesn't show anything.
Hello?
Show some wave dipole.
There's four. Chris,
Hello?
and who, do you have any questions? I don't think
Thank you. Okay. That's all right. We'll have some